Okay, so what I hope to have convinced you in the previous lecture is that depending on the energy of the particle, the orbit or trajectory it will take will be different. And we considered the various trajectories the particle could take for a specific potential, an attractive 1 over r squared potential. We'll have a look at one more example. It's the eternal mannequin of theoretical physics, the harmonic oscillator. For which case the potential energy can be written like this. And that implies that the resulting force from this potential has to be equal to minus k over minus k multiplied with r. So this force is quite different from the previous force we considered, in that as r goes to 0, this force vanishes, whereas in the previous case it diverged. And similarly, as r becomes large, in this case the force becomes large as well, whereas the potential energy, whereas the force in the previous case would vanish. So let's see what happens here. Let's consider first a scenario which is probably familiar to most of you. Namely, consider first the case where we have 0 angular momentum. So you have just a particle moving in this potential. If the angular momentum is 0, v prime is equal to v, since the renormalization term vanishes. And the potential energy looks something like this, which then implies that if the particle has an energy E, which now has to be positive, since the minimum of the potential energy is 0. We see that we have one turning point here, R1. So the situation is symmetrical for, you can think of this as a circular cross-section. So the motion is bound. And if there's no angular momentum, it means we have a rectilinear motion. Which also will be harmonic. So it goes like cosine or sine. So that's a well-known case where we have 0 angular momentum. But consider now the more interesting case where we have, in fact, a finite angular momentum. So we now have 2 contributions to V prime. We have the harmonic oscillator potential, but we also have this term stemming from the conservation of angular momentum. So we have these two terms that make up the total the total potential energy. And if we add these terms, we should get something like that. So let's now consider what happens if we have a particle with energy E that is moving in this effective potential V prime. Well, again, we see that there are now not one, but two turning points. The particle cannot escape into this or this region, since in those regions the potential energy would be larger than the energy. So it's confined to this region. So we actually can get bound trajectories in this case as well for the harmonic oscillator. And there's one special case which I would like to mention in particular. And that is if you have a force which is written like this. So we now have movement not only, say we have movement in a plane. So we can decompose this total force into an x and a y component, but both with equal constants. So it means that the harmonic oscillator has equal frequencies, both along the x and y direction. So this situation describes two harmonic oscillators, or a superposition of them, which are perpendicular to each other. And in this case, we get our ellipse. We get an elliptical orbit. So that's a special case. Okay. Now, we're going to, as I mentioned in the previous lecture, we're going to have a look at an exact solution for the generalized coordinates for a particle moving in a central force or a central potential. So we're going to have a look at, we're going to solve exactly for r of t to see how this motion really looks like, instead of just making a qualitative sketch. But before doing so, we're going to take a detour to something known as the Varial Theorem. The Varial Theorem is a quite general theorem which is related to the statistical properties of a many-body system. The Varial Theorem is quite useful because it's valid for several types of physical systems. And it is a theorem that is related to the statistical properties of the system, and it's associated with the time average over various quantities. So we're going to derive this theorem. And let's first define our system. And we're making a quite general description of the system. We're saying that we have a system of point masses, or at least objects that can be considered as point masses for our purposes, in positions Ri, and that these masses are all affected by forces Fi. So the Fi is the force acting on particle I. Newton's second law can be written like this. And now let me define this quantity G. It's the sum over all particles, and the summand is the momentum dotted with their position. So it might seem a bit artificial to introduce this quantity at this point, but you'll see why it's useful. So the time derivative of g would look like this. So let's see if we can simplify or identify these terms. The first term looks like this. And the momentum is given in the usual way. Oh, sorry. Should be a dot there. So we have two velocity vectors. So we have mass velocity squared. In other words, the first term is simply 2 times the kinetic energy. The second term, unfortunately, we cannot manipulate very much. It's simply given as the sum over F dot R. So we have that the total time derivative of g may be written as 2 times the kinetic energy plus this force term. Now, let's see what happens if we take this equation and average it over a time interval tau. And I denote the time average by this overhead bar. And by definition, the time average should be the integral over the quantity from 0 to tau, and then divided on the norm of the time interval, just the length of it. So if I now insert the g dt into this integral, I would just get that. Now, this we can't simplify much further, but this we can solve. by the fundamental theorem of calculus, this integral is equal to this. Since it's written like a total time derivative. And now we can actually make a useful observation. So my claim to you is that this right-hand side can be 0 under some specific circumstances. So when is this right-hand side equal to 0? Can you see any scenario where this is the case? Yes.
Well, if this is some sort of periodic something with a period tau, then it will be 0, please.
Okay. So you mean that if g is a periodic function in tau,
Yeah.
then g of tau should be equal to g of 0. Yeah. So that's one case. RHS is right-hand side. So if g is a periodic function with tau, then the right-hand side is equal to 0. And for g to be periodic with tau, it would mean that we have some sort of periodic motion. And we can see this based on the definition of g here, that if r, describing the position vector, is a periodic function of time, then momentum should also be a periodic function, so that g is a periodic function. So that's one case. There's one more case, at least. So we have that the right-hand side is equal to g of tau minus g of 0 divided on tau. Well, would you agree that if we have a fraction where this term is finite at all times, and we let tau go to infinity, it should vanish? So if tau goes to infinity, whereas this term remains finite, this should be 0. Importantly, in this case, we can relax our assumption about periodic motion. This argument does not assume periodicity in any way. We're just saying that as long as Ri and Pi are finite at all times, then G has to be finite at all times. So if we let tau go towards infinity, the right-hand side should vanish. And one thing that we can immediately conclude is that our system here has to be confined in some way, because we need finite position vectors. the common thing for both of these cases is that we obtain that the average kinetic energy, average over a long period of time, should be equal to minus 1/2 of this term. So it's valid both for periodic motion, but also for non-periodic motion, as long as Ri and Pi are finite. And we have a sufficiently long time interval. And it's a quite powerful argument because we haven't made many specifications. Our system so far is quite general. And we now have a direct statement about the average kinetic energy of the system. So this is the Varial Theorem, and we'll have a look at 2 examples of its application. And the first example is an ideal gas. So imagine we have some box here which contains an ideal gas. And the unit vector n here represents a unit vector perpendicular to the walls of the box. And let's assume we have a volume V and a large n number of atoms. How many of you have had thermodynamics? Okay. So you probably heard the Equipartition Principle. The Equipartition Principle states that the average kinetic energy for the system has to be 3/2 times the number of atoms multiplied with kBt, where kB is Boltzmann's constant and T is temperature. And I realize now that T is a bad choice for a symbol, so let me call it curly T. And the content of this equation is basically that the average thermal kinetic energy of a particle is 1/2 kBt at a temperature T. And if you have n atoms, and each atom is allowed to move in 3 directions, it becomes 3/2 n kBt. Now, we would like to relate this kinetic energy to this side of the equation in the Varial Theorem. So to do so, we need to say something about the forces acting on the particles. And if we have an ideal gas, we're basically saying that there are no interactions between the components of the gas, the atoms. So if there are no interactions, there should be no forces between the particles. So do we have any other forces in the system if we neglect gravity? Yep.
Force of change of momentum when the particle is hitting
Exactly. These walls actually constitute a constraint in the system. So the force of the walls acting on the particles when they hit them is a force, which is relevant to us. So Fi is the force exerted by the walls, and we can actually say something about the magnitude of this force. Because the force exerted by the wall on the particle should be equal but opposite in direction to the force exerted by the particle on the wall by means of Newton's third law. And we know what the force exerted by the particles on the wall is. It's given as the pressure, or the infinitesimal force dF for an infinitesimal area dA. So let's just consider an infinitesimal area on the wall. In that case, the force, the magnitude of the force would be P dA, where P is the pressure. And the direction of the force should be minus unit vector, because it's acting inwards. So now we have an expression for the force, which we should be able to insert here. So to obtain the total sum over all forces acting on all the particles and dotted with the position vector, we would have to integrate over the entire areas, over the entire area of all the walls in the box, which would give us this. So we're basically assuming here that this sum can be turned into an integral. All right? Now, this part can be mathematically rewritten. Can be rewritten from a surface integral to an integral over volume if we take the gradient of the integrand. So this is basically a standard theorem in mathematics. I think it's called Stokes' theorem. I'm not 100% sure. Yeah. Now, this term is just equal to 3. If you act the gradient operator on the position vector, you get 3. And so, altogether, we should have 3/2 minus 3/2 p, and then the integral over dv, which just equals the total volume. Okay, so let's see what we've accomplished here. We have the Varial Theorem. We have an expression for the average kinetic energy related to the temperature of the system and the number of constituents. And we now also have an expression for the right-hand side of the Varial Theorem related to the macroscopic properties pressure and volume. Vt is a Varial Theorem. And we obtain this equation, which you may have seen before. It's just the basically thermodynamic equation describing an ideal gas, relating pressure and volume to temperature. So you can actually derive this equation by using the Varial Theorem. This is Boyle's law, by the way. We'll have a look at one more example. This is a quite general situation. We're simply considering a force which is written as the gradient of some potential. So this is very general. So the question is now, in systems with this type of force, what information can we obtain from the Varial Theorem? So it's basically a conservative system. Just to get an idea of what we can expect, assume that we have one particle in a central field. E.g. here means exempli grata, it's Latin. So it means basically, for instance. In this case, we have that the average kinetic energy is equal to this. Assume now that we have a potential energy which can be written like this. It's a constant multiplied with r raised to the power of n plus 1. And this might seem as an artificial choice, but consider that depending on what n is, we're actually able to capture several types of characteristic potential energies. For instance, if n is equal to minus 3, we get, and a is negative, we get an attractive 1 over r squared force, like we considered previously. And if n is equal to 1, we get essentially a harmonic oscillator potential. So this is still quite general. So if this is the potential energy, the force, has to be proportional to r raised to the power of n. And we get the following relation here. And so this equation now tells us that for a conservative system and a particle moving in a central field, the balance between the average kinetic energy and the average potential energy is given by this. So the average kinetic energy is directly proportional to the average potential energy, and they're related through this factor here. So if n is equal to -2, for instance, we have a so-called Kepler potential. And the Kepler potential is something we're going to consider in much more detail. In this case, we obtain a factor of -1/2, relating the kinetic and the potential energy. And if n is equal to 1, which means that we have an harmonic oscillator potential, we have the quite neat result that the average kinetic energy is exactly equal to the average potential energy in the system. So these two examples should give you an idea of how you can use the Varial Theorem to obtain information about sort of the content of kinetic energy and potential energy in the system. And next time we're going to have a very detailed look at the Kepler potential and what kind of orbits we can expect from such a force. All right.